Hello everyone. In this video, I want to show you another interesting thing in vibrations called the beat phenomenon. So you can see that in a system with two DOF that has two natural frequencies very close to each other, or in general anywhere that you combine two harmonic functions that have equal amplitude and close frequencies. Let me tell you an example here. So one is, let's say you have two pendula, right? Pendulum 1, pendulum 2, very similar, or in this case identical, right? So both have length L, mass M. The only difference between them are the angles, theta 1 and 2, and where they are being hung, and then at a distance a from the pivot point, you have a spring that is attaching them together, because if you don't attach them, you don't have a 2 DOF, you have a 1 DOF, two systems with 1 DOF. So we connect them with this spring, like simple masses that you connect with the spring. So here you connect them together, but the K that you use is small k, and I'll tell you why. This is not a really strong spring, it's a weak spring. So here, if you write the equations of motion for the objects, you get these two equations, and it's very easy to see why. If you look at any of these pendulums, so let's say this second pendulum here, right? Here you have the two forces of the pin. You can call them like AY and AX, right? And then you have MG down here, and you have the spring force. Now here you can assume one angle is bigger than the other. So let's say we say theta 1 is bigger than theta 2. That means this spring is going to pull this pendulum to the right, and it's going to pull back this first one, the one on the right, to the left. So in this case, you have this force here, and this force equals K times the displacement of this point minus this point. And here, if we assume that these thetas are small, so we go with a small assumption, right? So we make them a linear vibration. Then the displacement of this point can be simply approximated by this distance A times tangent of theta 1, theta 2, and tangent can be approximated by the angle itself. So you simply say A theta 1 and A theta 2. So it's going to be times A theta 1 minus A theta 2. And now if you take sum of the moments about point A, right? Sum of the moment about point A, and this angle here is counterclockwise, so we go counterclockwise positive. That is equal to this mg basically has this distance here, which is L times, in this case, L times tangent of, or sine, doesn't matter, both of them are theta. So it's going to be L times theta 2, right? And times mg, and clearly the moment of mg about that point is clockwise, so it's going to be negative mgl theta 2, and then the moment of this spring is positive, so that is going to be positive the force, which is ka times theta 1 minus theta 2, if you factor out the a, times this distance, which again, if you look here, this distance is basically the same as a, or a cosine theta, which is just a. So you can have a squared. And this is equal to what? This is equal to I about point A times alpha 2, which is theta 2 double dot. And this I about this point is clearly what? It's this mass m times this distance squared, so this is going to be ml squared, right? So you get this equation if you simplify it, and you can write the one for the other one, and you get this one. So these are your two governing equations, clearly linearized with small angle assumption. Now you can write them in matrix format, so you can write them as matrix M times vector theta double dot, where vector theta is both of these two, and matrix K, right, times vector theta equals 0. And as you know, in vibrations, in order to find the natural frequencies, we multiply M inverse by K and set the determinant of this to 0, and that will give us natural frequencies. In this case, if we solve for natural frequencies, we get the first one to be square root of G over L, the second one square root of under square root G over L plus 2K over MA squared over L squared. And the two mode shapes that you will get are interesting too. One of them is 1 to 1, the other one is negative 1 to 1. So if you want to write them as a vector, one of them is like 1 and 1, the other one is like negative 1 and 1. Okay? So these are the natural frequencies, these are the mode shapes. Now, let's take a look at these. So in the first mode, if you look, since the displacement is 1 to 1, right, then both of them will basically move like a single pendulum, because the amplitude of the displacement is 1 to 1. So if this guy moves 2 degrees, that guy moves 2 degrees. This guy moves negative 2 degrees, that guy moves negative 2 degrees. So they move together, linked together like a single pendulum with the frequency square root G over L, which is the frequency for a single pendulum. So the system breaks down into like a single DOF really in this case, but in the second mode shape, they move in the opposite directions with this frequency. So if this guy goes 2 degrees, this guy goes negative 2 degrees. If this guy comes closer, this guy also comes closer. Okay, well in this case, they go like this. So you have this mode and this mode, okay, with their natural frequencies. This is still not the beat phenomenon yet. I would just, so far we derived the mode shapes and the frequencies. Now, here we choose this denominator in the mode shapes as 1 and 1, as we said here, we chose them. If you do that now in response to some initial conditions, like what? Like theta 1 to be equal to theta 1 at time 0 be equal to theta naught, and everything else to be 0. So all we do is, in this system, we move this first pendulum to some degree. This one, we keep it in place. This one, we just move to some angle. And then from rest, we release the system, okay? In that case, we know always your responses with only initial conditions in free response is a combination of what? Is a combination of the first mode shape and the second mode shape, right? So what is your first mode shape? Your first mode shape is this with that frequency, and what? The second mode shape times what? The second frequency. So it is going to be what? It is going to be a ratio of 1 to 1 with this omega 1 and a ratio of 1 to negative 1 with omega 2. And this is the response that you have. So look, a ratio of 1 to 1 with frequency omega 1 and a ratio of 1 to negative 1, as you can see, with frequency omega 2. And there are 4 constants to be found here. One is C1, the other one is C2, then the phases phi 1 and phi 2, where they come from what? These 4 initial conditions, of course. Okay, so these are responses to this initial condition, right? Okay, now here we do a little bit of trigonometry. So if you look here, I have the formula cosine A and cosine B, right? And cosine A and cosine B you can combine together, right? Remember that here first, before I combine, I want to determine the C1, C2, phi 1 and phi 2 using these initial conditions. If you do that, if you plug in, so let's say plug in 0 in theta 1, you get what? You get C1 cosine of phi 1 or negative phi 1, which is the same, plus C2 times cosine of phi 2, right? That is equals to theta naught. And then in this bottom one, you get C1 cosine of phi 1 minus C2 cosine of phi 2. That is theta 2 at 0, which is 0. And then you have to take two derivatives. So you get four conditions and 4 equations, or 4 unknowns and 4 equations, and then you have to solve for them. If you do so, these are your solutions. These are your exact solutions. So you'll find C1 to be 1/2 of theta naught, C2 to also be 1/2 of theta naught, and then both phases will be 0. Okay, so in this case, right, you'll get this. And these are your solutions. Now here is the chance to do the trigonometry manipulation. So for cosine, because they have the same amplitude, so you get cosine of omega 1t plus cosine omega 2t, and cosine of A plus cosine of B can be written as what? Can be written as 2 times, let me write it for you, cosine A plus cosine B can be written as 2 times cosine of A plus, or A minus, doesn't matter, the order doesn't matter, A minus B over 2 times cosine of A plus B over 2. And you have this 2 and you have that 1/2 which cancel each other, so you get theta naught cosine of omega 2 minus 1 over 2t times cosine of omega 1 plus omega 2 divided by 2 times t. And similarly here, you have cosine of A minus cosine of B, which, as you can see, it can be written as 2 times sine of A minus, or negative 2 times sine of A minus B over 2 times sine of A plus B over 2. Okay, and that 2 and this 1/2 would cancel each other, and that negative of A minus B comes into the sign, so it becomes sine of B minus A, which you can see here. Instead of omega 1 minus 2 is 2 minus 1. So you get these two equivalent terms. These are exact solutions, this one and this one. Now here, we add some notations. This average frequency here, this one, we call it omega average, and this subtraction of the two frequencies, I call it omega B. So omega 1 minus 2, I call it omega B. Okay? In that case, the exact solution can be written as what? The exact solution can be written as your theta 1 of t equals theta 0 cosine of omega B over 2 times cosine of, times t of course, times cosine of omega average times t, and theta 2 of t equals theta naught sine of omega B over 2 times t times sine of omega average times t. And you know that a sine can be written as a cosine, right? Plus what? Plus a phase shift, right? So this sine, I can write it as cosine if I want to, right? Omega average times t, and a minus pi over 2. So basically now what I can see in both of them is a cosine of omega t function in both of them. One has a pi over 2 phase shift, and the same amplitude theta naught, which is changed according to cosine omega b over 2 and sine omega b over 2. So one of them I can say this is the amplitude, the other one this is the amplitude. And both of them are cosine omega t harmonics, again one of them with a phase shift, where their amplitudes are modulated by what? Their amplitude are not constant theta naught, they are modulated by cosine omega b over 2 and sine omega b over 2. Okay? Yes? Now, what is omega b? What is omega average? Here is the part that we assume the spring is weak, which means k is small, or the term ka squared is smaller, much smaller than mg over L. Now you might say, why that? Because we have these two terms in the omega 2, right? If you look here in omega 2, we have these two terms, right? If we multiply both of these terms by ml squared, right? If you multiply both of them by ml squared, one of them becomes mgl plus that one becomes 2ka squared. And again, you have to multiply by ml squared, divide by ml squared, right? So you can write your omega 2 as this, right, under square root. This is divided by square root of ml squared. So now you see these two terms appear in here, and if we assume that k is small, this term can be neglected compared to this, right? And you can approximate your omega average. If you do a Taylor expansion, you can approximate your omega average by square root g over L, which is this frequency of a single pendulum plus this extra term. And omega b, which is the difference, you can approximate it by this. Okay, and you can do that. You can do a Taylor approximation and just go with the first term, and you can see that. So when we say neglect, not really neglecting is what we're talking about. It's just approximating. So you consider this as a function of a, and you so you write it as a function of a, and then approximate it as f at a of 0 plus a times f prime, right? At a of 0, approximated by a linear term. These other terms just neglect. And if you do that, then you get these two frequencies, right? So if you want to get some nicer formats, but in general, as you can see, if you look at the responses look very interesting. As you can see, they both look like they have the same frequency. What frequency is that? That's the omega average. They both have the same frequency, omega average. So this t here, the period of the oscillation, equals basically 2 pi over omega average, right? So that is what you have. And it's not just a sine and cosine, so it doesn't have constant amplitude. The amplitude starts from theta naught or goes at max to theta naught, but it's modulated by sine and cosine omega b over 2, as I just showed you over here, right? And you know sine and cosine, their max and min are at -1 and 1. So sometimes your amplitude is theta naught, sometimes it's negative theta naught, sometimes it's 0, because the sine and cosine becomes 0, and that is what you can see, right? So it's a sine function for which the amplitude is modified or modulated by these envelopes. And this envelope here, and this envelope, these are from what? For one of them comes from cosine of omega b over 2t. And for the other one, this envelope here comes from what? Comes from sine of omega b over 2 times t. Okay, yes, you see it starts at 0, here it starts at 1. And you clearly see there is a phase shift of pi over 2 between the two signals, right? This is a pi over 2, not time equal pi over 2. This is a phi angle of pi over 2, as we expected. So it's like two waves that are coming at each other. There is one wave and there is another wave, and they come together and they have basically identical frequencies or very, very similar frequencies. And at some points, the waves are reinforcing each other. So you get what? You get big amplitudes, like here. And at some other points, as they move across each other, then their max and mean will be added together. You get these nodes, you get these zeros, right? But as I said, sometimes this one and this one will go on the top of each other and you get this. Or this one and this one will go on the top of each other and you get these. Okay, so this is that beat phenomenon. Okay, where you have kind of like one frequency, amplitude of it modulated by another one. And you see this kind of interesting response in the physical system. Okay, so this is the beat frequency, and as I said, it's not just limited to this system. In any system, 2DOF, as long as these two frequencies right here, this omega-1 and omega-2 are close to each other, then we can say what? We can say this phenomenon can happen. And here, as I said, if this term is small compared to the other one, then you simply get the square root of mg over L over mL squared, which is going to be g over L. So you see omega-2 and omega-1 are going to be what? Very close if, as I said, this term k is small. There is a weak spring linking them together. Just as the last thing to say, there is another example if you want to see here, and this is called the Wilbur force spring example. And in here also you have a mass. This mass is attached to a spring, and it can have two different motions, pure translation and pure rotation. And the frequency of the translation is similar to frequency of the rotation. So if this guy has a k for up and down motion, and it has a k torsion here, and this guy is m, right? So one of them can be square root of this k over m, and the other one is going to be like I, so you also need I. So I times theta double dot equals basically negative kt times theta, right? And you can see that square root of kt over I is the other frequency. So if these two frequencies are very close to each other, then again in this system, because the translation and rotation are linked both through this spring together, then you can have a similar behavior in this spring. You can also see it in the airplane propeller, right? If you have a two-engine airplane, that is a propeller. So in here you have this propeller 1 on this side, and you have another propeller on this side, and they generate frequencies, they generate harmonics, sound waves that are very similar in amplitude and close in frequency. So the wave that they generate here, they go in all directions, the sound wave, right? As they reach each other here in the middle, those waves at some points they are what? Reinforcing each other. At some points they are basically canceling, destroying each other. So you see that the sound wave they generate, the noise that they generate, sometimes if you hear to it, it goes very loud, and sometimes there is no noise. So the noise that you hear in these engines, in these airplanes, sometimes is loud, sometimes is what? Very quiet, and it keeps changing. So you hear that beat phenomenon also in sound waves generated by, as I said, two-engine prop airplanes. So this is a physical example of that, other than these masses and pendulum. this is this interesting phenomenon that you can see here. That is the beat phenomenon here. So hopefully this video was useful to you and you learned something new. As I showed here, all of the pictures, equations, text, everything is taken from the book Elements of Vibrations by Leonard Meyrovich, which is a very good vibrations textbook. And hopefully this video was useful to you. So I'll see you in the next video. Thank you.